optical fibers. All the others have a pretty big region of melted, melted center. Yeah. The influence of the polarizations, as I said before on the previous studies, the grating was perpendicular to the polarizations. So we saw that our first level of grating, which is it is perpendicular to the polarizations, but the second level of grating that overlaps over it seems to be parallel to the polarizations. And when we change that polarizations, it is affected the same way than the first level. We tried thermal treatment on those gratings to see if it was a reversible phenomenon. So we tried 1 hour, 6 hours, and 10 hours treatment at 180 degrees, which is a bit lower than the glass transition temperature. We also tried a 4-hour treatment with 200-degree temperature to see what would happen. And here are the results. First of all, the 1-hour treatment didn't change anything on the structure, well, anything visible. The 6-hour treatment really decreased the height of the structure to 23 nanometers. And at 10 hours, we obtained 17 nanometers. But at the 200 degrees at 4 hours, the gratings were completely erased. But it was really a short period for our thermal treatment. So we decided that that thermal treatment was a bit more efficient and to a good pace at 180 degrees. It would less affect the overall structure of our class. So our preliminary results on optical fibers. The fiber is of the same class of AS2S3. It is a multimode fiber. The diameter of the core and cladding are 100 and 167 microns. Sorry. The exposure, as I said before, we use the ideal parameters that we obtained. So we use 10 milliseconds and 0.2 millijoules for our exposure. So that's our first result. It wasn't what we expected. There's only gratings in this region of the cross-section of the fiber. The gratings are really not well defined. As we can see here, there's a lot of crossings between horizontal and vertical grating. So we tried a different approach, or well, we just put the fiber a bit closer to the lens. So we thought that the energy dispersion would be a bit more uniformly distributed. But as you can see, we obtained quite a strange structure on our fiber. We yet don't really know what happened. We obtained on other tests the same kind of structure, but it is clearly not the same kind of grating that we obtained before. It is really wider with a period of 3.25 microns. So in perspective, we need to obtain a bit more data on the ablation rate and the ablation thresholds to clearly determine the energy we need to use to do the ablation under glass. We need to do some exposure at the lens focus for the see if the grating period decreased. Also, some exposure after the thermal treatment, recreate our gratings, and compare the new and previous structures with structural analysis of that. The fibers went to subject the glass bulbs to the same thermal treatment than the optical fibers, and retain the ideal parameters that we obtained before, because we think that the fiber might have had a kind of different structural change when it was melted to get to the fiber state. In conclusion, the conditions for nanostructure creations were optimized on my glass. The grating forms are perpendicular to each other, and the two levels are equally affected by change of polarizations. Thermal treatment is efficient and to a good pace at 180 degrees, and preliminary test show the possibility to inscribe grades on the optic fiber, which is quite a promising result. But we need to do a bit more work on that field. So, thank you, and if you want to know a bit more about the group, I invite you to go to our web page. Thank you. Yes.
In your idealized case, you're showing the spherical profiles, but it looks like in your experiment the profile was off, which would definitely affect the reproducibility of your results and probably your gradings as well. Is this something you controlled for, or how do you do something?
What do you mean the Gaussian profile was off?
Well, I mean that you didn't have a spherical profile.
Yes, but we measured the profile when we did the exposure. It was it was aligned and it was not really off the Gaussian profiles, except we don't know why the glass interact not in the way of the profile.
But even in some of them, you were seeing that there was like a definite, like they were like this cut in half or something. Like the profile of the laser looked. Maybe I'm.
What do you mean cut in half?
It looked a little bit inconsistent, no? So it might.
And this pop.
The femtosecond lasers were a little finicky. Did your folks controlling the profile, or you took the profile each time before you did the experiment?
No, not each time. No.
Okay. No, that's great. Thank you.
Any other questions?
So,
yes.
I almost forgot my question, but the first question is that if you want to summarize basically what defines the height of the gradient.
What defines height? Yeah. It's a bit difficult to say. I think there's two models to explain the interaction. I wouldn't be able to explain what makes the difference between height with different exposures. Might be the with more pulses. There's more a periodic structure created in the plasma, but I wouldn't want to take well, I don't have the information about that. Yeah.
Okay. The second question is, what's the direction of the light?
These are
the direction of the light that you shine to the fiber. Is it perpendicular, inside, or?
No, it is. We put the optical fiber the same way that we put our samples before. So when we cut the fiber, the cross sections is really perpendicular to the light. Yeah.
So this is just a guess. I'm not sure, but do you think that the effect can go back to the slide that you have the picture of the fiber?
Yeah.
So I'm guessing there's some kind of lensing effect on the borders for the light.
Yeah, maybe. Weren't sure about that. Might be a possibility. But we didn't get any of that effect on our previous result.